Now in chapter 13 of the King textbook, we'll take a look at strings, right? Strings are just going to be characters strung together in between double quotes. We've seen those with Hello World. They're also going to be character arrays. All right, string literals, right, are simply a sequence of characters enclosed within inside double quotes, right? Just like we saw our message Hello World in our first program. So anything we put inside double quotes we'll consider to be a string. In this case, the word string is inside double quotes. Here, we just have a blank space. And here, it's an empty string. So double quotes together will form an empty string. We'll see later when we might have a use for that. Otherwise, you can type any character. So any character that can display on the keyboard, any character that can display on the monitor, anything you can type on the keyboard can go inside of sets of double quotes. So they're simply a sequence of characters. Right. And things you might not have known before about printf is that you can continue a string over to more than one line. So this code is found in example 1C. So here's an example of string continuation. We just pop up that example here to make it a little bit easier to read in terms of the keywords. Right. So we can see with this printf, we start here with this double quote. And then to continue the string on more than one line, the simple backslash character is put there, right? This doesn't have to be all the way to the left. I could have tabbed it over here if I wanted. And let's see, if I throw this, if I add this file to the active project, right? Pull out this other one. So here, if I save that change, I compile, no errors, and sorry, it's still compiling. Yeah, not sure why that's quite so slow right now. So here, let me finish. The backslash here then shows us more than one, or more than ones, or continuing the same string on different lines. So notice here, starting double quotes, ending double quotes on next line. You have to have the backslash character here to separate it. Otherwise, this example shows starting double quote, ending double quote, but the hello or printf still considers this one string. The rest of it is continued on another line. Here's the rest of the message. All right, so let's build and run that. Right, and it actually, in this case, still prints out our message simply because now notice how I added these spaces in here. See this big space we have here? Let me go ahead and put this all the way back over now. If I do that, it considers there to be a lot of spaces on this one continuous string. So now if we build and run, right, we can see then the only space we had was this one here between the E in line and the backslash character. Right. So those are just ways, if you have long messages in printf, then you can continue things on more than one line without calling printf multiple times, or in this case, right, you can put several strings together within the parentheses. So either one of these then will work. And we consider these to be string literals because they're inside double quotes. Now the data type of those string literals is a char star. And we know that char is a data type, star means that this will be a pointer. So a string literal its data type will be a pointer data type, a char star. And if you look at the function prototypes of printf and scanf, you can see the first parameter in the list should be of type const char star. Remember, this const modifier here means that whatever we put will be read-only. So const with a pointer means the data that it points to is read-only. Same way with scanf, that first format string we put in there that needs to go inside double quotes, its data type is char star, const char star meaning read-only. So that's why when we pass this string literal here, hello world, or any of the string literals to scanf, those are data types are char stars. And C simply treats them as character arrays. So it's going to then create, let's take a look at this example here. So char star A is the name of my array. Right? It's data type, it's a pointer, so A here is going to be a pointer to a char data type. That's what this asterisk suggests, right? when I declare this. And then the equal sign says, well, I want to assign to that this string ABC. And what happens is C will use 4 bytes of memory to store this. It uses 1 byte for A, 1 byte for B, 1 byte for C. 4 bytes because char requires 1 byte. That's why A gets 1 byte, B gets 1 byte, C gets 1 byte. And what it does, the 4th byte then is used to append this null terminator. So this \0 is the null terminating character. And that is always appended by C to the end of a string literal when we declare it like this. So it always uses 1 more char, or 1 more byte of memory, to append it with this null terminator. Simply because if you want to use some of these string literals with other string library functions, they will search for the null terminator being there. Right? So we normally append that to the end of our string literals. Right? So let's take a look at the string literal pointer example, example 2. Let's move over to code blocks here, where example 2 is. Let me add this to the project. Let me remove example 1. All right, so example 2 here. All right, I want to demonstrate that the null character is appended to the end of a string literal. So I'm declaring 2 char stars here. So A then is an array that points to this string literal ABC. W is another string literal that points to WXY. Puts will just give us a blank line. And here we're going to print out then A points to the address. And so remember, whenever we want to print out the address or what's stored inside a pointer, we use %p, right? So here, if I just use the argument A, it'll show us what's stored inside A, which will be the address where A points to in memory, where these are stored, A, B, and C are stored. Similarly, right, we'll print out what's stored inside W, and that will be the address that W points to. And then what we're going to do is we're going to walk through the array. Let's go ahead and run this and then come back and associate it with a code here. So let's take a look then at this code. So this first printf then said A points to address. This is the address on my computer right now, 00408-024, where this is pointing. Well, let's see. A, B, C, those are 3 characters, right? 3 chars. And a char, the size of a char is 1 byte. So we need at least 3 bytes of memory. But look at where W starts. W starts 4 bytes away at address 28. So you can see then that actually 4 bytes of memory were reserved for A. Right? We want to see, though, if the null terminator was appended. So what the loop does is the loop is going to walk through this code. Let's take a look here. So I've got this unsigned char I set it equal to 0. I said I less than 8. If I'm using 8 bytes of memory, that's why we're using the 8. And we're going to walk through and print the address then of the pointer. So %p, right, we'll substitute in here this A plus I. Well, remember, A points to the start of this array. So the address that A points to would be this same address where this character A is stored. So maybe I should have given those different names. So A plus I, well, when I is 0, remember that's an offset, so 0 bytes away from where this is stored. So we're going to see the address where this character A is stored. Then using the indirection operator, we're going to read what's stored at that location in memory. Right here, here's the A, and that's going to be printed out as the character. So %c says to take this argument and interpret it as the character. %d says to then take this argument here. So once again, the indirection operator with A plus I, and I want to show the ASCII value, or the decimal value that's stored in memory with that. So we get this output then. For each one of these addresses, we start where our pointer A is pointing, right? And we see then, there's that address. Here's what's stored in memory, the character A, and that's a decimal 97, right? When we increment I by 1, we go to the next address here, 25. We see that the character B is stored there, and then B's ASCII decimal representation is 98, right? The character C is stored here. Its ASCII decimal representation is 99. And finally, when we get to address 27, well, the null terminator can't display on the screen. That's why we're not seeing anything here. But you can see that its decimal value is 0. It's appending that null terminator. Similarly, since these are stored contiguously in memory, that's why I'm using this one array to walk through them, we'll see that then W points to this next string literal, WXY, that's stored at this beginning address, and we walk through it byte by byte and print out what's there. You can see at the end of it, it has the null terminator stored there as well. So the takeaway from this is when you then create a string literal like this, is you remember that an extra byte is stored in memory for that null terminator, that \0. All right. And there's the example output in the slides. All right, let's take a look at another way that we can do this. So we used the char star before. Another way you can do this that we've already learned, right? When we learned to create arrays, we've learned that we could then use this empty bracket notation and put an initializer list after it. Right? Let's pop up this example 3 code here, and let's add it to our project. All right, so example 3, right? This is simply the array notation we learned before, pointers, A. And we weren't working with characters. What we saw was something that looked like, well, let's say int, oh, I'm going to name this array, empty brackets, and then we saw we could use this initializer list, where if I said, oh, 1, 19, 4, that if we did this with an integer array, that what the compiler would do, the compiler would look at the initializer list and say, oh, there's 3 elements in the array, so I'm going to substitute this, I'm going to make this of size 3, right? And we can use this empty bracket notation. We did that for other data types. Well, we can do that for char data types as well then too, right? So we say char A empty brackets, we put this string literal out here, and it will still then create 4 bytes to store it. In the previous example, we did the very same thing by saying char star A equals ABC, right? So both of these methods then allow you to create a character array whose length is determined then by the number of characters inside the string, and then we'll have the null terminator appended here, right, for this one. Now, let's take a look at what the output of this is. Right? All right, so it used different addresses in memory on my machine, right? Notice that the address has changed from the previous example. And let's look at what happens when we're walking through the array. So we've declared A here first, haven't we? But notice that B here, or sorry, W is the second thing we declared. Notice that W has a lower address, right? This 28FF07 is lower than 28FF0B, right? So A actually got thrown onto the stack in a higher level address, right? The null terminating character is there, but when we walk through this, starting with the beginning address, we actually walk through WXY and then ABC. The null terminator is there. And the thing is that with this method, the null terminator is stored in memory, just like the other example, but things get stored in different areas of memory. So notice here we had a completely different address when we actually stored our other example. Here, oh, let me just wipe these out. So if we just change this back to example 2, where we had char star A equals ABC, right, and char star W equals WXY, right, and now let's build and run this. Notice we get a different set of addresses here. WXY, sorry, we get we get the 2.4 and the 2.8. Actually, the reason the WXY is showing up in memory is I'm using the W to step through this, and the other one I use the A. So let's change this to A, A, A. All right. So with the declaration, with this declaration, right, I get this const char star. The difference is it goes to a different place in memory, a different address, right? As I walk through, I still have the same information stored in memory. It's just stored in different places of the program memory. That's not real important for you to know at this time. The important takeaway from this at this time is simply to know that either of these methods create an array of characters for you, right, whose length is determined by the string length, and that a null terminator is appended to the end. Right? That is the important takeaway. Right? It's just that if you're playing with memory addresses, you'll get some different results. Right? And then we can use pointer notation then as well to modify some things, but in the case of constant char stars, you can't use the pointer notation to modify what's stored there. Right? So here I created an array, or sorry, created a pointer to a char P. Assign P to this string ABC. All of this is okay, right? Because this is a string literal that's thrown out into memory. I can make P point to that. But whenever I make P point to a string literal, then I can't go ahead and use the dereference operator to overwrite what's there. So here, where this says this is undefined behavior, I'm trying to store the character D to where P points. Well, P, remember, is going to point to the start of the string. P will be pointing to where the character A is stored. So this looks like I'm trying to store a D where the character A is. This doesn't work. And see, this is undefined behavior. So you don't want to try to do these things with constant char stars. It doesn't matter whether I use the character notation of the single quotes or the string notation of the double quotes. This is all undefined behavior. You can't use this array notation to do this as well. But what I can do is you can make P point to a completely different string literal. This isn't something you want to do. It's not a good practice. Basically, you're going to leave some other things out in memory that you don't want to be there. So we're usually just going to use our const char star. So remember, the data type of this string literal is const char star. You can't use anything to modify it. And that makes sense because if you remember it's const, it's read only. So you want to avoid then having a pointer point to something and reassign it later. Right. We can take a look at example 4, which basically has what the slide has in it here. It just has a few more comments. I'm going to close that down and not save that. Right. All right. So here I'm declaring a pointer P to a char. Right, and I'm reminding you when we do this, P doesn't yet point to any area of memory, so it's pointing to garbage. We have learned that to be safe, we could go ahead and make this point to null, but that would make our program crash if we use P uninitialized. Right. And now if we want to make P point to something, here I happen to then make P point to that const char star. So remember, this is a const char star here. It's going to store the characters A, B, and C in the null terminator, so it'll use 4 bytes of memory. And we can read from a const char star, but we can't write to it. All right, so here we're just going to go through and use the array notation, P at index 0, 1, and 2, to read what's there. We're also going to use then the indirection operator with a pointer, and then some pointer math to read what's there as well. So both of these are going to read from the same area of memory. P at index 0 points to the same place in dereferencing P. Right? P at index 1 points to the same place as P plus 1. P at index 2 points to the same place as P plus 2. Here we use the array bracket notation. Here we use the indirection operator. Right? And if we were to run that, right, we could take a look at this. right? The data stored in P at index 0 is A, dereferenced P is A, P1 is B, P2 is C. And you can see each one of these individual notations produce the same results, right? The next thing that this program is doing is showing you then the address of where P is pointing. And this is talking about the cases of things that are undefined behavior. So undefined behavior means while it may look to run in your program, it won't always work consistently. Because undefined behaviors, C doesn't guarantee what's going to happen. It may appear to work, but you don't want to count on that. So anything that's undefined behavior, we never write that in code, right? But down here, this is where we're getting the output that the address of P is where P is pointing. Notice here, this was legal for me to reassign P to this other const char star, but when I do, notice that this string AB has a completely different address, AC, 4080AC, than this other string. Basically, this other const char star is sitting there somewhere in memory where our program can never get to it again. Right, so we've lost some information in that sense. Right, so that's just to show you, if you use this to point to something else, you can never go back and get this to point to that unless you save this address somewhere else in your program. So we tend not to do that. Once we make a pointer point to a string literal const char star, we tend not to make it point at anything else to avoid any sort of undefined behavior or difficult to debug behavior in our programs. Right, so your big question should really be, when should you use string literals? A lot of times we use them to display messages. Sometimes our program, we have some error messages that we want to display. It's easy to define those, especially sometimes as global information or to pass information to and from one function to another. Right, we use %s then to display strings. Right, we've seen that before with printf. So what we could do is we could create these different messages then and display them with printf. Right, that's more likely when you're going to use a string literal. Another common way to use a string literal in a function is if you want to convert some things that are characters to other values or numbers to values. Let's take a look at this one. So we want to write a function that converts the hexadecimal integer values. So 0x means hex, 0 through f to their character equivalents. Right? I want to be able to print out a capital F, right, when I have certain hexadecimal values. An efficient way to do that is to write a function that returns a char value. That particular char value happens to be, its index array value happens to match then what that hexadecimal character would be. So in other words, if I pass this any sort of digit 0 through 15, I'm going to return the hex equivalent to that. Let's take a look at that in code. All right, so I don't have an example of that. Let's just go ahead and open up main and see where we could use that example. All right, I'm going to copy paste in this code. All right, so what I want to do here is let's write a loop. We're going to have I cycle through from 0 to less than or equal to 15. And printf. So we're going to say, we'll show the decimal value, decimal percent, let's use 2D, right? And hexadecimal percent 2s, actually, let's just use C here. We're going to use C because this function is going to return a char. And so now I just want to print out the value of I. Then I'm going to call the function digit to hex char, that's the name of my function. I'm going to pass it my digit I, and it's going to return when I is a 0, it's going to return, this is character 0's at index 0 here, character 1's at index 1 here, character 2's at index 2 here. So it's going to use this string literal, right, with this index notation. So digit here, when digit's 0, it'll return this at index 0. When this index is 1, it'll return this character. So this is a sort of a clever trick you'll see that some people use to convert decimal numbers to their hex equivalent. Right? Now we know that we can use printf to print out that information without resorting to this trick. There are some ways that people use this because they need to insert it in other strings, so they'll use it for that. But I just want to show you the idea here of using a string literal in combination with this index notation to just pull out information that we need from this particular string. That's the overall purpose of this. And actually, I don't think I've added this to my current project. Oh, and I did not put a new line character here. Let's put a new line so we can see these on every line, or one per line. And I forgot my semicolon. All right, so you can see, right, as we go through our loop for the decimal digits 0 through 15, decimal numbers 0 through 15, we call this function, we passed it the value of I was using the index here, so it printed out these string values. It returned this char here, right? The printf then converted that value at return, showed us the character value for that. So as I said, this is just a way of showing that you can use some sort of string, use the array notation to access the individual characters in the string. Now let's take a look at using scanf then in this case. So here's something that's going to cause your program to crash. So we've declared this pointer MSG, right, is a pointer to a char, and we're printing out enter message, scanf in this case. Well, this, we know that a char star is a string, so we said let's just go ahead and enter something and then print it back out. The problem is when you create this pointer, you've allocated memory for this particular variable, pointer variable, but you haven't allocated any memory for the string to point to, and that's where your program is going to crash. Let's see if that's here. An example, no, that's not example 5. Let's pull this out of here and run this in main. So let's overwrite what I have in main here. All right, so once again, we're creating a pointer, right? But it doesn't point to anything in memory, right? We haven't allocated any memory for this to point to. Let's go ahead and compile this, right? And this is where you should pay attention to your warnings, because here, this says MSG is used uninitialized in this function, right? Meaning, uninitialized means that we have, it's a pointer, we haven't made a point to any area of memory, right? If we ignore that warning, so if I build and run, all right, I'll just type in hello. And eventually, I get this message that my program, so the name of this project was strings, the executable then is strings.exe, has stopped working because it can't access any memory to store this in. All right, so that's just a common error when you first start working with pointers, is that you'll declare this and forget to reserve any sort of memory where the message that you type in can be stored. Right. Right. Here's how we want to do this then. Right. We want to go ahead then and create memory. So now, in this case, if I just make message, MSG, an array of 10, that's going to allocate, well, 10 times the size of a char is going to allocate 10 bytes. And if we run this version of the program, right here, sorry. If we run this version, we should be able to type some things in without it crashing, right? So, all right, so now we have, so if we compile, right, we don't get a warning, build and run. Well, then if I type in hello, right, it stores it and prints it back out like we expect it to. All right, now let's talk about what happens if I type in something that's a string that's more than 10 long. So let's build this, right? So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So it's going to read all of these in as characters, right? And notice then it read all of those in. Well, when this was running, the operating system was evidently nice enough to give me some extra memory so it didn't crash, right? Nothing crashed. But I want to do something to limit this because I can't guarantee that will always happen. I also can't guarantee that I won't be overwriting some other area of memory, right? Take a look at what happens here. If I say char, oh, I just need to give this some name. I'm going to call it name. What if I go ahead and give it 3 bytes of memory? So let me just run the debugger here. All right, so now we can see that message then looks like it's just this null terminated string. So what happens is we don't initialize this array to anything, a char array. Usually what it does is it will then put a null terminator in the first position. There may be some in other positions. It may initialize the whole thing to that. In this case, we've got at least the first one initialized. Here, the first one was initialized, and the rest of the array was initialized to 0. All right, but notice what we have here. All right, so let's just go ahead and say next line, next line. I'm going to go back again and type my long string of numeric characters. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Now let's come back here. All right, so now we can see here in message, all this did, all we can see here is 0 through 9. But yet when we go to print it out, and it printed out that entire string. Right, probably because the debugger said, hey, you're only allocated 10 spaces. I'm going to show you all 10. It didn't appear to overwrite what was in name, yet somehow it saved some extra memory out there. We can't guarantee that that will always work. I was trying to look to see if maybe it would overwrite what was in name. It didn't appear to overwrite that, but we can't guarantee that. So we want to be very careful then in terms of when a user is entering information from the keyboard. If we've only allocated 10, the space for 10 there, we want to limit what we read in. And we can do that then by doing this. Right, if we limit the number of characters read here, so message is still declared as 10, but now if I limit this to 9, I'm limiting it to 9 so I can leave 1 for the null terminator in there, it should stop reading after we type in 9. So let's go ahead then and take a look at this example here, which I believe is example, no, it's not example 5. Oh, let's just copy it from the lecture slide, throw it here into main. All right, so we're going to limit this now with this width specifier to 9. To build and run, let me stick with my 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And we can see now, right, it only then took 0 through 8, which are the first 9 characters, and then it would have put that, or it would have null terminated the end of the string. Let's go ahead, do a run to cursor so we can pop up the debugger. Let's type again 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Right, you can see here now, right, what's stored in message are 0 through 8. We limited the fact that we read in 9. right? And if we were to execute this next line of code, which we've already done, we saw that it printed out, that's what was a message, right? All right. So the takeaway then here from this example, right, when you're working with scanf, if you have a limited size array, limit the amount of characters you can read in so that you're not writing things in areas of memory where you shouldn't be. Right. So out of this section, some of the important takeaways then were the fact that if you write something like this, it's a string literal, right? Anything we write, any characters inside of double quotes are considered a string literal. And then the data type of this is a constant char star. So data type of these string literals, right, is a constant char star. And the other important takeaway from this that you'll most commonly use is creating some sort of a character array that has memory, right? And when you want to use scanf to store things in there, you want to limit the size. Those are the two most important takeaways from this. The other things are things you should be aware of if you try to start working with pointers, but in terms of this class, what we'll commonly do, limiting the size of scanf reading in a string, and then that a string literal is a data type of constant char star. Right, that's the end of this section on strings. We'll start working with string variables in the next section.